Good afternoon, everyone, and welcome to today's session on deep learning. As we had discussed yesterday, today it will be a demo class regarding your object detection algorithm based on YOLO, and that will be taken by Rahul Sharma. He's an undergraduate from Punjab Engineering College, and he has done his recent project on remote sensing with the help of satellite images. So I welcome you, Rahul.
Hello,
Hello.
am I audible?
Yes, Rahul, you are audible.
Okay. Thank you, Sakshi. So let me know when I can start.
Yes, you can start. If you want, we can wait for another 2-3 minutes. Otherwise, we can start now.
Okay, all right. So let me share my screen there.
Yes. Okay.
My screen visible? Hello.
Yes, Rahul, it is visible.
Okay. Good. So just a minute. Okay. So today we can discuss about YOLO object detection. And in this, what I will discuss about is I will cover up how YOLO detection works. So like what goes into the detection part of the YOLO when the image is fed into it, what all steps it performs, and finally it outputs an image that shows the detection with the classes, right? And after that, I will also explain about working with YOLO, in which we will try to set up a system, our own system with the YOLO model and create our own custom dataset, configure the YOLO, and try to train and test accordingly. And finally, I will show you a demo of it as well. So let's start with the first part. So how YOLO detects. So for YOLO, so if an input image is given, then what the YOLO does is it divides that image into a S by S grid. It can see here. So if this was our input image, so this is divided into this S by S grid. Now YOLO performs two steps of it. First step is like it creates a class probability map. So what this class probability map means that for given each grid cell, what is the probability that it has a class C. So if like in here there are three classes like this dog, cycle, and let us say this car as well, or any other like trees or bill. So if there are I'm considering only three dog, car, cycle. So for each grid cell there will be a kind of a probability map that this cell predicts this cell has dog with this much probability, like PD is the probability for dog, P PB is the probability for bicycle, and PC is the probability for car. So this is like the probability that it corresponds to each grid cell. So this is like the class probability map. It's bluish means that it thinks that these boxes contain the dog. This yellowish is like if these contain the cycle, and this pink is like that yes, this area contains some carbon, right? So this is one thing that is called class probability. And second is the part of localization, where it has to detect a bounding box around detected object and output that with the confidence score. So that is bounding box plus confidence. So we will now discuss these two parts further. So first in it is something called feature map. So what does feature map is? So given given grid, that is S by S grid, for each grid cell, there will be there will be some there will be some dimensions corresponding to it. It will give some output. So what each grid cell has it has five. First, there are five attributes, four of which are the coordinates Tx, Ty, Tw, and Tx. There is an objectness score which is represented by P naught, and after that there are some class probabilities. So depending upon the number of classes we have, that much class probabilities are generated for each grid cell. This is for each grid cell. And finally, each grid cell can use to detect up to some number of bounding blocks. Let us represent that number by B. Right. So this B represents that each grid cell. So if this is a grid cell, it will have these parameters that let us say like this dx, dy, dx, dy, dw, dw, dh. Okay, so is my voice not audible? Hello. Okay.
Sir, you are audible, but your
Not
voice is
clear.
not clear.
It's not clear.
Okay. Just a second there. Hello. Now is it clear?
Yes.
Yes, sir.
Hello. Okay. Right. So this is like a grid cell, and it has these parameters dx, dy, tw, th, p0, and p1, p2 up to pc. Right. This is corresponding to one bounding box. And now, if say let's say that this grid cell detects b bounding boxes, so the dimensionality will simply multiplied by b. There will be b such dimensions for given grid cell, right? So if I have to say what will be the final dimension of feature map, it will be s times b times 5 plus c, where this 5 corresponds to these 5 values, and this c corresponds to these probability, these class probability values, and b is the number of bounding box that grid cell detects, right? So like in this example, right? So this is an example, is an image of a bird that this image contains a bird. So the image size is 416 times 416, and let us say this grid cell. This is the grid cell, right? For corresponding to which we get these attributes, which are the box coordinates. Actually, these are uh, not correct to say these are box coordinates. These are some neural network outputs that are used to generate box coordinates. We will talk about it in further. Right. So these are those 5 values which are generated. This is class score depending upon C, and if there are B boxes, that is then it is multiplied by. So like in previous slide, it's 5 plus C times B, right? And since this is for a single grid cell and there are how many grid cells? S into S. So this will multiply to S into S. So this will be the feature, right? Right. Now moving on. Now let us talk about something called confidence score. So this confidence score, or better known as class confidence score, so this tells us that what is the probability that the bounding box our YOLO algo has detected, it contains the class C, any class C, right? So it has two things which you have already seen. So first is that objectness score. Objectness score means that the bounding box that the algorithm has chosen, whether it contains an object or not. Right? That is just the probability of whether the bounding box has object or not. Right? If it has objects, what is the probability that it is of certain class C? That is called as class probability. Right? So this is simply the problem of conditional probability. First thing we will check is P0, that is whether the object, the bounding box has an object or not, which is termed as objectness score. Then, if that bounding box has the object, what is the probability that it is of class C? That is P. So, using the conditional probability, if we have to detect the what is the class confidence score of class C for a given bounding box, that is simply given as objectness score multiplied by class probability. Right? So if I write more properly, it is like probability. There is some class C given the object. What is the probability? There is some class C. This is that PC factor. This is that PC factor, and then there is this P object, which is that given bounding box as an object. So this is that P naught, if it has object, what is the probability that it is of class? So this is given as something called confidence score or class confidence. Right. This is this is called this is called class confidence score that is given for corresponding to each bounding box. Right. And you can further check it out in the paper given by J. Redler. You know, Lookmark's unified real-time object. Now this was the like part one of our problem. Right? Now let's move on to the part two of our problem. So that part two of the problem is like we already know that how if a given bounding box, how we are going to calculate the confidence of that bounding box for a given class. Second problem is what is the bounding box? Where we have to localize the bounding box, right? So the second part of the problem is to identify the location of the objects in a given image and indicate their location with the help of a bounding box, right? So this is the part two of our problem. So like for a given example, so for this input image, we want something output like this bounding box, right? So we will see this example, how this bounding box is generated by you. Now, there is something called as anchor boxes. So anchor boxes is like, these are some predefined or also known as prior boxes. These are some predefined boxes that are defined as a tuple of width and height. So what does it mean is that uh, instead of uh, instead of generating bounding boxes like a blindly, we use anchor boxes as our starting point for the part of object detection. Right? So these are some very defined boxes, and these boxes are fine-tuned. Instead of we generate the absolute values, we try to generate some coordinates, some offsets that are used to fine-tune the bounding boxes, which are applied on these anchor boxes. So these are nothing but some predefined boxes which are fine-tuned to generate the original bounding box that we want as an output. So if let's say that PW and PX is the width and height of the anchor box, so this is something we give during training. Anchor boxes are given during training that yes, these are the anchor boxes that the YOLO algorithm should use to fine tune to generate the bounding box on a given image. And how it will generate the bounding box depends on these. So let us say that PW and PH is the width and height of an anchor box. And we already see that the YOLO algorithm generate these four coordinates, right? TX, TY, TW, TH for a grid cell. And let us say that for that grid cell, the top left corner is CX and C. Right? So the bounding box coordinates, that is the center X, center Y, width and height, that will be given as these form. So Bx is sigma times Tx plus Cx. By is sigma times Ty plus Cy. Bw is Bw e raised to power Tw, and Bh is Bh e raised to power Tx. Here this sigma is, it's a sigmoid function. It's a sigmoid function. Right. It will be more clear with an example. So let us consider this example. So let us say this was our grid, and let us talk about this grid set. Right. This grid set. So this dotted black line you see, that is the anchor box. That is corresponding to this grid cell. So the center of this anchor box lies here in this grid cell, and this is the PW and TH that we have already given as our anchor priors to the unit. And the CX and CY are the coordinates of this one. CX and CY. Right. Now to get the center point, what we will do is we add the offset to these CX and CY, and that offset is again this TX, TY that was generated from the YOLO and is present in the feature map. These values are used to detect the center as well as the width and height of the box. So using that same conversion, so this offset is detected by applying the sigmoid function on Tx and adding it to Cx, and this one, and the height coordinate, so the y coordinate is detected just changing the Tx to Ty and Cx to Cy, and this is the final width represented by VH and VW, that is detected by the algorithm. So as you can see here, it make use of the anchor box to tune that to give a bounding box to this blue bounding box, right? And the sigmoid function is given as sigmoid of x is 1 over 1 plus power minus something like this. Okay? So something like this is the sigmoid function. So now you know how using the anchor boxes, our YOLO algorithm generates bounding boxes corresponding to each grid cell. Right? Now let us take an example and try to generate bounding boxes. So for this example, this is an image from the COCO dataset. So COCO dataset is it is a Microsoft Common Object in Context dataset that has some 80 classes. So 80 classes of objects are present in this dataset. Right? And this is one of the images that we have taken. And the input size of this image is 773 times 500. Right? So firstly, we are going to resize it to 416 and 416. So choosing these values depends upon the network review. The resizing depends on the network. What is the network resolution uh, that the data model can accept to work upon, right? So depending on that, these values are this resizing is done, and then we are going to divide it into a 13 by 13 grid. So this is the resizing part, and this is 13 by 13 grid that is created by you. Now next. Now we are considering that each grid cell is going to generate 3 bounding boxes. So we have taken B as 3 and we will generate 3 bounding boxes. So as shown in this example. So these are the 3 bounding boxes that are generating corresponding to this grid cell. So this is the grid cell and corresponding to this grid cell, here is the center. These 3 bounding boxes are generated, right? And this is corresponding to only one grid cell, and since there are like in this case there are 13 into 13 grid cells, so you can clearly see that there are going to be many bounding boxes that are going to be generated for each, because for each there will be 3 bounding boxes. Like for this there are 3, for this there will be 3, this there will be 3, this there will be 3. So number of bounding boxes will be something corresponding to 13 times these many bounding boxes will be generated by the queue. This is like the maximum number. Depending upon what is the objective store, it can further be reduced. Right? So, like already said, there will be multiple bounding boxes that will be generated for the given input. So for this case, if there are 13 S is 13 and number of bounding boxes generated for each grid cell is 3, so that ends up some 507 bounding boxes maximum. And now if I ask you about the dimensions of the feature map, what it will look like. So this is the S times S. We have already seen this formula. This is the number of bounding boxes. This is that 5 number that corresponds to box coordinates plus the object store, and this is the number of glass. Right? So the feature map dimension will have this dimension 13 times 13 times 3 times 5 plus 3, which is 43,095. Right? So these contains this feature map will contain all the information about the generated bounding boxes. For that, for a given bounding box, what are its coordinates, what is the objective score, what is the class probability that that bounding box corresponds to, and the class probability that has the maximum score, that is considered as the output. You will see from it. Right. So for visualization, this is just for visualization. This will be something the algorithm will offer. You can see that there are multiple bounding boxes, right? And the one of the problems that comes with this type of bounding box equation is it is very much rarely possible that most of the bounding boxes are just redundant. They are not worth of detecting the object. And second thing is that it is possible that multiple bounding boxes detect the same object. Right? So, like in this example, I will show further. There can be like 2 bounding boxes or 3 bounding boxes or more than that that are just detecting the same object, and that is like not right, because we want only one bounding box corresponding to one object in our final detection. Right? So to overcome this problem, there is something called non-max suppression. So non-max suppression is the next part, the YOLO, that helps to remove all the redundant bounding boxes. And if there are multiple bounding boxes that are just detecting only one object in the given image, hello, right? So that is detecting only one object in the given image. So the rest of the bounding box will just be discarded. How it's going to work, we will see further. So now let's talk about non-max suppression. So what are the steps that non-max suppression performs? So as we have already seen, there is a parameter of objectness score, the feature one, right? So first filter that is applied is there is some threshold we set. So in this case, we are taking, let us say that threshold is 0.6. So what we say is that bounding box that have threshold of less than 0.6, simply discard them, do not consider. Right? If this is P not yes, but so this filter is applied on this parameter P. Right? And other thing that also is there is let us say if P naught is 0, that for some bounding box the algorithm has detected P naught is 0, so we actually don't care about what are the rest of the values, because those values are of no use to us, because it has already said that there is no object in this bounding box. So those bounding box are also not generated. Like we discard them. So we already discard them in previous step, for which the P naught is 0. And after that, whatever the bounding boxes are left, considering on the objectness score, if that is less than or equal to 0.6, we simply discard those values. Right? And for the remaining boxes, now whatever the remaining boxes are left, they perform two steps. So first step is these steps are performed for each class. This is for each class. Sorry. Each class C. Let us say same for each class. If there are 80 classes, this step is going to be performed for all 80 classes. Right. So what are these steps? We are going to pick up that box that has the largest PC. For a given class C, we are going to pick up that has the largest confidence pool PC that is already explained in the previous slides. And that PC is going to be output as prediction, right? So we say that if there are multiple bounding boxes that corresponds to a single image, we select one that has the largest PC and say that this is the bounding box that predicts the given class C with the confidence score, whatever is calculated. Right? Now for the rest of the bounding boxes that also detect the same object, we need to suppress them, or in other words, we say we need to discard them. So we have already studied something called IOU. IOU is intersection over U, right? So for the generated, so for the taken bounding box PC, if we have taken the bounding box PC, let us say this is the PC and this is like some other bounding box that is detecting the same object. So just this is the object, right? So one bounding box is this, one bounding box is this, that is detecting the same object. And let us say that this has a probability of 0.9 and this has a probability of 0.7, right? So what we want, but firstly, what we will say that this 0.9 probability bounding box is responsible for the detection of this object. And now we want to suppress these bounding boxes, right? For that, we will use IOU factor. We are going to calculate the IOU of this other bounding box with the one we chose as the prediction. If that IOU is greater than or equal to 0.5, then we simply remove this bounding box. This bounding box is no more considered. Let us see like this. We simply remove this bounding box. And this is only what will be left. Right? So this is how non-max suppression works. Now let us see this in our own example. Right. So like this we have already seen. These are the number of bounding boxes that are separated. So like firstly said, the first step will be discard all those bounding boxes that has a object confidence objectiveness score of less than equal to 0.6. So this is it. So now we are only, as you can see, we are only left with 3 bounding boxes, right? So all the rest of the bounding box are discarded with, because their P naught was less than or equal to 0.6, and these are only the bounding box that are left over. Let us say that the confidence score of this bounding box is somewhere 0.9. These are some hypothetical values I am picking up. Right. So this inner bounding, this bounding box has a confidence score of 0.9. Let us say this has a confidence score of 0.7, and this third one has a confidence score of 0.85. Just taking it. Right. So these are the remaining bounding box. So for this case, we are considering only the class word. Right. We have assumed that the bounding probability of uh, this box detecting the word is 0.9, this box detecting the word is 0.7, and this box predicting the word is 0.8. Right. Now next step is to, like in MS, is to select those bounding box that has the highest probability, which will be this one. Which will be this. Just a second. This is the bounding box that shows the highest probability. Right. And we will pick this as the detection, as the local object localization for the word class. And so that would be detected. We selected the maximum of for the given class word. We selected the bounding box that shows the maximum probability of the class. So this was this bounding box. And now next step in the non-match suppression is to suppress all those remaining bounding boxes that predict the same object. Right? So these two bounding boxes are also pointing to the same object. Right? So we want to suppress these bounding boxes. Like I already told, the next step for us will be to calculate IOU of this yellow bounding box with the remaining 2 red bounding boxes. Right? So I have already calculated that. You can take this up as an exercise and just consider some values for these and center values and try to calculate the IOU. Right? So the IOU of that yellow bounding box, this yellow bounding box with the other two red bounding box are 0.84 and 0.77. So for this, it came out to be 0.77, and for this one, it came out to be 0.84. Right? And since this IOU is greater than the threshold we chose, that was 0.5. Right? So they are going to suppress it or discard it. Right? So this is the finally that will be left. So this is how YOLO performs its object detection steps. Right? And this is the final. So if I talk about what is the use of this non-match suppression, is like firstly I have first thing that I have already said is that we want to suppress the bounding boxes. But one question could be that since we already know that we are going to select the maximum bounding box, simply discard the rest of it without applying non-match suppression. That is one thing, but this covers another thing. If let us say, so one thing is that this wherever, like this was the grid cell, let us say this is the center. So wherever the center of the given bounding box line, whichever grid cell the center of the bounding box line, that grid cell is responsible for the detection of that object. And it is very much possible that there are multiple objects that have the same grid center. So if I take an example here only, so let us say this is this is some person, and there is some car-like object in the background, right? So for this image, if I right, so this is the image that I'm considering, that there is some uh, like human being here and a car here, and let us say that this grid cell is going to be responsible for the detection of both the objects, and they have the same center. Right? So, what we don't want is that we don't want to suppress the bounding box that corresponding to same grid cell, that corresponding to same grid cell, that is for the some other object. So here non-bit suppression will help us out, right? So if why it will help us out, because the shape of the bounding box for this car-like object will be elongated rectangle, horizontally elongated rectangle, and for this human it will be like vertically elongated rectangle, right? So for these type of detection, what will happen is if for let us say this is one of the object detection for the human as well. So this bounding box is going to suppress right. So this bounding box, this one, is going to suppress this bounding box, and it is not going to interfere with this because the IOU is going to be very less. So when IOU is less than 0.5, that means that the other bounding box is detecting some other object in the same image. Right? So this is another useful thing that non-bit suppression helps in. Right? The first is it suppresses the bounding box that detect the same object, and it doesn't suppress those bounding box that have that detect different object in the same given image. Right? So now moving on. So now we are done with both the steps, both the tasks that are required for the final detection. So we have done the bounding box localization and the class confidence score calculation. Thus now we have finally detected an object in an input image that will be output like this. Right? So this is the word. So the YOLO has detected that this is the bounding box for the bird, and it is not visible. This is 0.9, and it has detected with the class probability that this bounding box contains a bird with a class probability of 0.99. So all in all, this is what are the major steps that YOLO performs in its detection. Right. So now let us talk about few things these are in view of YOLO V3. So YOLO V3 is a but new version, or let's say we have a new version of V4, but we are talking about V3 in this. So this was given by Joseph Redmond and Ali Faridi. So what they did is they used a darknet 53 backbone as the YOLO V3 architecture. So what does this 53 signify? 53 is nothing but the number of convolutional layers that the model uses. Right? So they use 53 convolutional layers. And the example that we were running previously was for YOLO V3 only. So the YOLO V3 has a network resolution of 416 times 416. So like we already saw that if a given image is of a higher resolution or a lower resolution, the network is going to resize that image according to the network resolution. So in the given example, it was 772 times 773 times 512 was the input image. So it was resized to 416 times 416, right? And the one important thing that it has is that YOLO V3 detects at 3 different layers, right? So earlier it was like only a 1 layer detection, but now there it was a 3 layer detection. So each there are 3 layers of YOLO, and each layer uses 3 anchor boxes. Right? So what are say letter like these are the 3 layers, 1, 2, and 3. Right. So at 3 scales, detection is performed with 3 anchor boxes. Right. And the grid cell of each layer is like this is say 13 by 13. which we have already seen. Next is 26 times 26, and next is 52 times 52. Right. So these are the grid distribution which we are talking about here. Right. So these are the three layers at which it is going to detect, and for each layer there will be three bounding boxes. Right. So the example which we took previously, it has we took only one, considered only one grid size of 13 by 13 and considered bounding boxes of three. Now what you have to do is just take two more layers of 26 times 26 and 52 times 52, and for each layer define three different anchor boxes. Right. So it also uses three anchor boxes. It also uses three anchor boxes. It also uses three anchor boxes. So in total, the number of anchor boxes used by YOLO V3 are 9. Right. It is going to use 9 anchor boxes or 9 prior boxes that are going to be fine-tuned to detect the object. Right. And grid size is 13 times 13, 26 times 26, and 52 times 52. Right. And this 13 times 13 is responsible for large object detection. So depending upon the types of object, they can be categorized into small, medium, or large. Right. So 13 by 13 is responsible for large object detection, and that's why the types of anchor box we want to choose for this 13 by 13 layer will have some scale, will have a bigger scale compared to 26 by 26 and 52 by 52, right? Which are responsible for medium and small object detection, respectively, right? So one question that I might ask is that so what will be now the dimension of the feature, right? So we have already seen the dimension calculation, how is it done, right? We have already seen for that 13 by 13 grid with 80 classes and three bounding boxes. So this is left in as an exercise. Think about it. That would be the dimension of the feature map for the YOLO V3. Right? So this is all for the YOLO V3. Now let's move on the working with YOLO. Now let us try to set up the YOLO for ourselves and try to play around with it, or do our own custom object detection. Right. So setting up YOLO. So if you want to set up it locally, that you need to perform some extra steps in it. Right. So you would need a good GPU because it is a quite powerful model and it requires GPU processing. Otherwise, or a powerful computer, otherwise it just simply don't perform good. So you need to, for your local setup, you need to have a good NVIDIA GPU that has a CUDA support, and you need to set up CUDA toolkit and CFDNA library. So you can refer to the official NVIDIA CUDA site where they show where they have the complete installation process of setting up your system with CUDA. Right. And second thing that you might need, this is optional, this is open source. So during training, if you want to see how your training is going on, to check the progress of your training, some visualization tools, so that is open source. That can be used. Other than that, if you don't want to go through these steps of local setting up your system for YOLO, you can simply choose a Google Colab. So Google Colab Notebook has already set up their system. They have good GPU support, and that can be used for your training and testing purposes. The only drawback that Google Colab is that there is some time put up, something around I think 12 hours after which the support ends. So you need to wait for some time to again restart it. Right? So, so the setup that we are going to perform, we are using the Ubuntu system, and we are going to Ubuntu 18.04 system on which we are going to set up the user. Right? So we have already configured this NVIDIA GPU with CUDA support and OpenCV. So this is just to verify your NVIDIA installation. This is simply a command. This is simply a command that you can run in the terminal. NVIDIA minus SML. So this is going to be something the output you should see. This is the driver version, the CUDA version, NVIDIA SMI version, and all that. Right. So this will verify that you have your CUDA setup properly. Right. So we are going to use the repo of LXC daily. So Alexi Jimmy is also the one that was proposed a better YOLO network. That is YOLO before, and he has also proposed scale YOLO before. That are new versions of the YOLO that are used for detection. So in this report, we have all the implementation of YOLO from version 1 till the latest scale YOLO before. There is also YOLO V5, but that is not present in this report. So we are going to use this report to configure our YOLO V3 object detection. Okay. So simply clone this report using the get clone command in any directory you want. So here we have cloned this repository in documents. Okay. So it will be saved as a will be saved in the folder target folder in documents. Right. So next, depending upon your system, you can make changes to your make file. So there will be some parameters of GPU, OpenCV, and CODM. So simply, if you have your GPU, OpenCV, and CODN set them to 111. Otherwise, you can keep them 0. So if you keep them 0, then the model that YOLO is going to run on your central processing unit or CPU, right? And not the GPU. After you have configured this make file, simply go to the directory, darknet directory, open the terminal, and run this make command. So this make command will compile all your source files that will all your source files, and depending on the configuration, you will set up your CUDA to work with YOLO. And if it will take some time, but if everything are satisfied and there are no issues, then no error should happen. Right? Now your YOLO setup is complete. So this same steps can be performed on Google Colab, and the same the procedure will remain same. The difference is that you have to set up CUDA here other than Google Colab. So, like I already said, this repo has all the latest implementation of YOLO from V1 till scale YOLO V4. Right? So now you are done with this setup. Now what you can do is you can either play around with it by downloading already trained bits. So we are going to consider YOLO V3, and that is already trained on the MS Coco dataset, and you can get those bits by simply running this command wget. This is this site of the original author of the YOLO V3, and he has already given the YOLO V3 pre-trained weights for this is for Coco dataset. So you can simply download this and check out how the YOLO performs detection on these simple objects like car, bus, motorcycle, aeroplane, bird. Right. Otherwise, what you can do is you can create your own custom dataset, and you can train that and test these YOLO models. So next we will see how we can set up our own custom dataset for training. Right. So for each image, so like if when you have a custom dataset, you are going to have some n images, right? So first thing that you want to do is for each image, you need to create an annotation. What annotation means is that you have to mark the ground truth bounding box that will be used by the YOLO during training to train its weights depending upon the labels that you have provided for those training images. Right? So for each image, you are going to create a .txt file that will be in YOLO format. So if let us say that your image name is xyz.jpg, xyz.jpg, then you need to create a label image, a label text file of same name that will be xyz.txt, and keep both these in same folder. So you have to perform these for all the images in a given folder. There will be an image file, and then corresponding to it will be a text file. So text file will be in the YOLO format. And what is YOLO format? YOLO format is a tuple of type. So the first value is object class. Second is the center of the ground truth, center x of the ground truth, center y of the ground truth, height of the bounding box, and width of the bounding box. Right. So this is the YOLO format. And other thing is that it will be in a scale of 0 to 1. Right. So the text file will contain the information about the bounding box if that between 0 and 1. So it will just normalize the width and height of the image to 0, 1, so that these values lies between 0 and 1. So this is the YOLO format. So for example, if a given image I have and yes, this class object. So this object class is going to be simply an integer. right, corresponding to a given class. So, for example, I have three classes. Let us say bird, dog, and car. Right. So, class label for bird is 0, class label for dog is 1, and class label for car is 2. Right. And I mark that given image. So this is the given image. I choose my these grounding bounding boxes in it, and how it will be saved. I am just showing like for this, the tuple will look something like if this is for bird. I am assuming this is for bird, right? So the YOLO tuple will look like the class object class is 0, its center, which is this. So normalizing it between 0.0 to 1, let us say it is 0.0005, 0.001, and height is 0.02. Oh, sorry, width is 0.02. Oh, sorry, there needs to be change. This should be first width, and instead of width here, it should be width. Just interchange the width and height in the tuple. And 0.0. So this is the tuple corresponding to this bounding box. Similarly, there will be a tuple corresponding to this bounding box. There is going to be a tuple corresponding to this bounding box, right? And for this given image, these tuples will be stored in this txt file. This was xyz image. So these bounding box will be saved in this txt file, right? These tuples with these values, right? And for labeling, you would need an annotation. So the annotation tool that we are going to use is label IMG. That is again an open source annotation tool that can be downloaded from Python libraries as well or from the repo, right? And we are going to open an image in it and simply draw the bounding box around the objects, and it will automatically convert. That bounding box into the YOLO format and save that bounding box configuration, the bounding box label in the same folder where the image is contained. Right. So this is something that the label image label IMG graphical annotation tool is going to look like. So if this is an image and we are marking like so. So for this is a truck, right? So we draw a bounding box around this. There will be then after drawing a bounding box, there will be a window open that will ask for class label, right? That for this bounding box, what is the class label? That we are going to select it as truck, right? After selecting this as truck, so here there will be something like Pascal BOC or YOLO. We can switch between the YOLO. And finally, marking all our bounding boxes in the given image, we are going to simply save this text file. Right? So with this label IMG software is automatically going to save this text file, the same name xyz.txt that will now contain corresponding to xyz image the label information, right? So this is the part where we for our custom data set we do the labeling. Now once we are done with the labeling, the next thing we need to do is we need to configure YOLO so that it can work with our own custom data set, right? So how YOLO configuration looks like. So depending upon the number of images you have, you need to divide those number of images into some training images, validation, or testing. So ideally it is like or not ideally, generally it is like 70-30 or 70-30 or 75-25. This is mostly that is taken as training and validation testing percentages. Right? So depending upon the number of images, you can decide for your own data set which looks good. You can divide your training set into this in which we have our image and our text files. We are going to put it in a folder data/obj. So this is the folder where we are going to put our custom data files, that is xy, all those with xyz.jpg and xyz.txt. Right. If there are n images, then there are going to be these ntxt file, and these are put in this folder data/obj in the darknet. Right. And we generate something called train.txt and valid.txt. You can create a Python script and simply select like first 75% of images as training, or 25% of images as validation, or instead of selecting first 75, you can randomly select some validation, some 25% validation images, and keep rest of them as training images. So right, so this information is stored in training.txt and valid.txt. So the content of training.txt and valid.txt will contain the relative path to the images, relative paths of the images location, because which will look like something data/obj/image underscore name.jpg. Right, so this will be something like it is going to be present in train.txt and test.txt. This is the relative path, and all these images are already, we have already put in this data/obj. That's why data/obj and the image name.jpg. So these will be present in train.txt and valid.txt. Now these will be used by our YOLO model. So for that, we will create two more data sets. So two more data files. So one is obj.data and the other is obj.data. So obj.name is nothing but class.txt. Oh, so yes. So this classes.txt is a file that contains the name of our classes. So like I already told in this, that bird is 0, dog is 1, and bird is 0, dog is 1, and car is 2. So this information will be present in this classes.txt, and this will be in the same order. If bird is 0, then it will be like this. So firstly the file we will in this file classes.txt, firstly there will be bird, in next line there will be dog, and in next line there will be car. So in the same order as that of the labels. So if this bird label is 0, it will be the first one in the classes.txt. The dog is second, it will be second in will be this second in this obj.name, and then the car will be third. So depending upon your data set, this text file is created, right? And this text file is same as this class.txt. This is copied into the file and saved as obj.name. And this is kept in the same data folder. This is present in data folder. And the second, there is obj.data. So this contains 4 values. Classes. Classes is the count. Like if here we have 3, so this classes will be 3. If you have some n, so instead of 3, that number n. So the classes refer to that number n. Train is the path of the train is the path of the data/train.txt. So that train.txt file that we have already created, we give that relative path in this obj.data file. And then this valid is that validation file, so that it can be test, or in our case it will be valid.txt, because we have created valid.txt, and the names. So we have obj.names that we have already created. We give that relative path to this file. And finally, there is backup. So this backup is a folder that will be used during training to store your notes. While training happens, it might happen that there are some issues, system shutdowns, or light goes off, something like that, and there is some system failure. So your training is not lost. This backup folder is present, in which your training weights will be saved after some periods. Right. So like after say 1,000 iterations or 100 iterations, your weights will be saved, and like after 100 iterations there will be last weights, and after every 1,000 iterations a new file will be created, something like this. These files will be sorted in this backup, so that if there is some training issue in can always restart from the point where you leave off. This will save time. Right. And so now we have configured that all the folders, all the necessary folders that are required. Now there is a configuration file. Right? So for every model, like for YOLO V3, V4, V5, whichever model you are going to, sorry, V5 is not present in this repository, but that is another repository. So other than that, V1, V2, V3, V4, scale YOLO V4, YOLO V4 mesh, whichever YOLO you pick up, you need to configure their configuration file. You need to change their configuration file. Right? And the changes that you need to make is, so in this case, we are going to change YOLO V3 configuration file. So if you go to a CFG folder, there will be a CFG folder there. And in that, there will be YOLO V3 dot CFG. Right. If you open that folder, you will see some hyperparameters there. We need to change those hyperparameters depending upon what type of data set we are using. Right. So first parameter is like there will be a classes parameter. So classes is going to be C, which is the number of objects that are present in our custom data set. Number of object classes that are present in our data set. So like we are already taking the example of car, dog, and bird. So it will be 3 parts, right? And then there will be 3 YOLO layers present that will be fall under the section YOLO. And there will be a convolutional layer just prior to this YOLO layer, right? So in that convolutional layer, we need to set those filters using this formula 3 times 5 plus C. And this formula we have already seen. This comes from the fact that this 3 corresponds to B, 5 corresponds to those 5 prediction values TX, TY, those TX, TY, TW, TH. These are those 5 values. And that class C comes from the plus C, that is this, that comes from the probability classes, probability score that are going to be calculated. B1, B2, to BC. Right. So we have already seen this feature map. So this is the feature map that is going to be created, and the dimension of the feature map is dependent upon this filter. So this filter is going to be fixed. That 3 is the bounding box B, because YOLO V3 uses three anchor boxes. So it takes 3 bounding boxes per grid cell. So that is the 3 where it comes from. I already told this and C. Right. So for our case, C is going to be 3 that we are taking up, and that will end up with filter of 3 times 5 plus 3, 5, 6, 8, 24. So 24. So we are going to set filters as 24. Right. And there is going to be 3 YOLO layers. For YOLO V3, there are 3 YOLO layers. So for each YOLO layer, prior to their convolution, just before there will be a convolutional layer, of those convolutional layer, we need to set our filters with these 24. If our class is 3. Right. And the next parameter that we have is max batch. So max batch is the number of batch iterations that we want to run on the data set to train. So right, so it is defined as 2000 times number of classes we have, or 4000. So if it is like we need to take the maximum of these 2. So if you have only one class object, then this 2000 times it will come as 1. So we usually don't take 2000. Minimum is taken as 4000, and anything bigger than that is considered good. So this is just an intuition to set initial max batches, but depending upon how your data set is, you might need more iterations, right? So these are like you should start with these minimum, these as the starting point of the max batches, and if you feel like your model can train further or it can improve further, go on, increase the max batch and rerun from the last bits. Right? Another parameter is steps that is given as 0.8 times max batches and 0.9 times max batches. So these steps, these step size, there is something called policy steps, and there are scales different. So during training, your learning rate changes continuously, right? So at what point it will choose which state is dependent by these policy steps. So these are set as 0.8 times max batch and 0.9 times max batch. Okay. After you have made these changes, save this configuration file with whatever name you want, or this only just change this YOLO weekly or sales. Right. So now we are done with labeling of our data set. We are done with setting up that YOLO folders, that assess YOLO folders and YOLO files, assess YOLO files, training files, obj.name files, obj.data files. We have configured the configuration file of YOLO v3 that we are going to use as for our detection. Right. So now we are almost done with setting up our YOLO for our own custom, configuring this YOLO for our own custom data set. Right. Now we will go on to training. So in that the same CLC file that we just made some changes, there will be a section called training. Right. So in that training, there will be some batch. There will be a parameter batch and a parameter subdivision. Right. So uncomment those, because depending on what you chose as the batch size and the subdivisions, your training time can increase. So if you have a very good GPU, you can pick a batch size of, usually it will be set as 64 and subdivision will be 16. This is for YOLO V3. You can change these depending upon the power that you have GPU. So you can either increase the batch size or reduce the subdivision. Or if you have a powerful GPU, by increasing the batch size, you will eventually reduce your training time. Right? So, but obviously that will be a lot more load on your GPU. So depending upon that, you make changes to it. So these and uncomment these parameters of training. Save this configuration file, right? And since now we are going to train, so we will be needing some convolutional weights. Right? So the number of convolutional layers are 53 convolutional layers, and there will be weights associated with those convolutional layers, right? So we want to use some convolutional weights as our initial starting point. So one point is that you can randomly initialize those convolutional weights, but that is not a good approach, because if we randomly initialize it might take more time to converge to the optimal results. So instead of randomly initializing the convolutional weights, we are going to use some pre-trained convolutional weights. Right. So again, you can use this command to download pre-trained convolutional weights. This is for YOLO. If you are using any other YOLO vendor, accordingly you can download their pre-trained convolutional weights as well. Right. And now these convolutional weights, along with our data set and our custom configuration file, we are going to train the model. So the command that we are going to use to train the model is ./darknet detector train obj.data path. So we are going to give that obj.data. We have created that path here, and in our case, it will be data slash. Okay, this is the relative path we are given. Dot data. So this is the relative path. This command is run in the darknet folder, like mentioned here. Go to darknet folder, run this command, and give the relative path of data path. Similarly, for this custom CLG path, give the relative path, let it be CLG slash YOLO dot CLG, or whatever name you have saved this configuration file as. Right? And finally, this is the weights path. So if you are training for the first time, like we have already downloaded this darknet 53.1.74 weights in this darknet folder, we are going to simply use this weights. Okay. Right. Simply giving this the name of this weights file. We are going to train our model. So now you can hit the command, hit the enter. This training command will run, and you can relax till this training completes. For if just an idea, so if you are taking max batch as, so this is what I observed. If max batch is 4,000, and yeah, so if max batch is 4,000 and you are using YOLO V3, so the training time is around 12 hours for YOLO. is on the system that I use at 18.4 with quarter of the 4000 GPU. So with the max batch of 4000, the training time was around 12 hours. Right? So yeah, this is also seems like a lot, but it's a lot faster and a lot accurate that is also mentioned in the papers that are published. Right? A better version of YOLO has already been there. You can also experiment with it. But again, if you go for YOLO before, training time increases by some 10 hours, ending up to 22 to 23 hours. But yes, results are far more accurate. Right? So this is something you can play around with. So once your training goes on, so this graph that you see here, this can be live depending upon the OpenCV if you have set up. So if you have set up the OpenCV, you will see uh, uh, real-time graph that will be created during the training, and this will be like the loss. This is the loss graph that is represented here. So you can see here the loss value is 0.8740. So depending upon the data set, this loss may vary. So in general, if the loss is less than 2, if loss is less than 2, then the training is considered quite good. But again, it is very data dependent. If the data set is very big, you will see a loss less than 1. But the data set is quite difficult or quite large, and there are a lot of objects, and those objects are pretty difficult to detect. And it is possible that you might see a loss of 3, somewhere in 3 or 1.5, right? So this is again data dependent thing, and generally loss less than 2 is considered, right? And if you just a note, if you use a command flag of MVP, there is an MVP flag as well. If you go through the repository, there is a command just giving an intuition of one of the command. So if you go for a flag MVP, there type MVP and keep pressing save. So you will in the same graph you will see something like this. This will be something like the mean average precision. We call this MVP as mean average precision. That is the run of the validation set. That again can be used as an intuition for how your training is performed. So the loss is also giving us the same information. This can be some extra information that can be used and can be used to evaluate your model on your test. Right? So now your model is trained. Now everything is done. And yes, one more thing: if your training for any reason stops, or there is some for your system goes shut down and training abruptly stops, you can always go back to this backup folder, and here in the weights bar, instead of now again starting with these initial pre-trained weights, wherever your training stops, go there, go to the backup slash underscore class dot weights. So this will be uh, whatever the last bits that the model has stored, that will be present in this backup folder. This backup folder. So instead of, you can use the same command to continue your training. Instead of these initial train bits, just go to that backup folder, give that relative part to the backup folder of the last weights, the last weights that are stored in it. Right? And your training will continue from that point onwards. Right? So saving you all those training, so saving your training that you have done, all the time that it has taken up. Right? So now finally, now all your training is complete. The final weights, after all the iterations have been done, the final weights will be stored in the backup folder. Now it is time to test anything. Let us test how the YOLO has performed, how it has trained, and what output it gives for a given input image. Right? So now the test command that we are going to use ./darknet detector test. Again, this is the data path, custom CLC path, the weights path. So these weights path is the train weights that we have that are saved in the backup folder during training. And then there is the image bar, the image on which you want to test your YOLO model. So like already in the previous, this is same as data slash data. This is same as CFG slash that we have configured, right? And this will be backup, and there will be something YOLO, whatever the name is there, and it will end with dot final dot weights. So these will be the final weights that can be used. One more thing, if you have used this MVP flag, so there will be some extra weight file there that will be dot best weights. If you go with the MVP flag, the algorithm will automatically, this model will automatically save the best weights file as well with that MVP flag. Right? Otherwise, whatever the final weights will be, it will be saved with with that name dot final dot weights. Right? And finally, this is the image bar, whatever XYZ image you want to detect on. To get that bar in here, relative bar. Right. And when you hit this command, you will see a prediction output with the bounding box 1. Okay, so I will now show you a demo. The system is working. I hope the system is working. I will now show you a demo. Yeah, so right. So now, so the demo I'm going to show you is this is on the Coco dataset, and I am already using the pre-trained weights of YOLO V3. So this is the detection that will be given by the YOLO V3 model. Right. So like I already told, this is the dot darknet command detected test cfg coco.data. That obj.data, the path of the obj.data that we have to give. In here, I have given it as coco.data. Then this is the YOLO V3 configuration file that I have given. And finally, this is YOLO V3 dot weights, the YOLO V3 weights that I am going to use. And this is the path of the image data slash eagle.jpg on which I want to test my model. Okay. And just a second. For showing you the output of the model, let me with the configuration. So this is the configuration file of YOLO V3. Like I already told, these are the parameters that we change according to our data set. Is max, batch, steps. Then there are YOLO, here YOLO. So YOLO in here, just prior to that, this is the convolutional layer in which we have to give our filters. So let us see how this 255 value is given here. So for each YOLO layer, there are 3 bounding boxes. There are five coordinates and 1 object score. There are 4 coordinates and 1 object score, and there are C class probabilities, right? So there is 80 class. So 80 plus 5 is going to be 85. And since there are 3 bounding boxes, so that 85 into 3, that will end up as 255. Right? So this is the number of filters that are mentioned in the configuration layer just prior to the human. Right? And there are 3 combinational layers. So this is 1. This is 2. We have to change there as well. And this is 3. Right? So 1, 2. Actually, these are the convolutional layers. These are the convolutional layers where we have to need to change that. Right? And there are other parameters as well. This defines the convolutional layers that within the convolutional layers that you do with the uses. So these are the anchors. These are the predefined anchors that we have already discussed about, as we already told that YOLO uses 9 predefined anchors. And then you can see here, these are the 9 predefined anchors: 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? this is used by the YOLO weekly play, YOLO weekly. Right. So now let us see how the detection performs. Right. Now if I click on the- Right. As you can see here, the model has correctly detected word in the given image, correctly detected word in the image, and it has detected it with 0.99 probability. If I show you a code that has dog, car, and duck in it, so see, this is an image that has three objects in it. So one is dog, it has detected. This is a cycle here, and this is the car, and these are the confidence, the class confidence that it has detected with. So 0.99 is like 99%, one is 100%, 94 is 94%. This is shows that this is stuck in the image. Right. So this is how YOLO V3 works, and this is how you can set up the YOLO models. Right. Yeah, so these are the references that you can refer to. These are first, these are the papers and the website that you can use to set up your model and to study further about how YOLO works. Right. So with this, we come to an end of the session. So any doubts? Any questions you want to ask? Hello.
Do we have any doubts? Anyone having any doubt?
So I see a question here. How do you count this demo in Windows? Yeah, for so since I have set up the Ubuntu system for Windows, you need to do some extra step that involves using the PowerShell, and you have to download something called CMake in Windows. So there, I I have tried in Windows, but it was a bit tedious for Windows to work out. Like Ubuntu was quite simpler to use. And there is possible you can set up in Windows. You have to use the PowerShell, and there will be a CMake, uh, a setup for CMake that you have to download, so that the process that is done by Make here. And yes, you have to also get the um, I forgot what was called. So yeah, what I'm saying is that you need to configure that CMake portion, the main portion that is in this version of Ubuntu. For Windows, you have to work around that CMake part, make all your source files or your object files for your program. After that, the steps for training and detection will be the same. The build process is a bit tedious in Windows. Right. If you have any doubts, you can ask. Yeah, Visual Studio. You will also require Visual Studios for your build process in that Windows. Your Visual Studios, your CMake, your CMake setup, and your PowerShell. These are the things that you might need. You can refer to this site, this GitHub repo of XCAB, who is also the author of YOLO Windows. He has explained the setup for both Linux, Windows, Ubuntu, and as well as how to set up tensor objects. Right. Any more doubt? Fine then.
Any doubt? Anyone? So
Good
Rahul,
session, Rahul. Very good session, Rahul.
Thank you, ma'am.
Sakshi, please continue.
okay. It was really a very good session. So I don't think there are more doubts. Then we can end the session now. Thank you so much, Rahul. And for all the participants, I'll share the attendance link in the chat window of your WhatsApp group today. So as soon as I upload your attendance in the WhatsApp group, kindly submit within next 10 minutes. We are not pasting the attendance link in the WebEx chat window today. It will be there in your WhatsApp group only. Thank you, everyone.
Thank you, Sakshi. Thank you, Rahul. Bye.
Where is the attendance list? Attendance form?
Share the attendance link in your WhatsApp group only today.
Okay, ma'am. No, same link.
Yes, I'll upload it in the WhatsApp group. It won't be there in
Oh,
WebEx.
okay.
Okay.
Thank you, ma'am.
Welcome.
Ma'am, please provide the attendance link on WebEx meeting group, WebEx chat.
Actually, it has not been generated yet. That's why we need to wait
Ma'am,
for some.
please copy the link and paste it
I
because
know,
I have no more step.
but it has not been generated even today. It will take some time.